Hey guys, this is your last page of notes for atomic structure and light. This is the fourth part, but we'll continue on this unit next class as well. So your question of the day is, what is the wavelength of a fish swimming in a pond with a mass of 2 kilograms and a velocity of 1.5 meters per second? So go ahead and try to do this on your own, and I'll kind of help you out here. Okay, so you need to use that new equation that you learned last class or on the video if I had you during that snow day, but it looks like this. So we have wavelength equals Planck's constant, which is this number. And then your mass, which is 2, your velocity is 1.5. So you need to multiply those two numbers on the bottom and then do Planck's constant divided by that number to get your wavelength. So I'll let you guys do that on your own. All right, so another problem with our model of the atom. Werner Heisenberg, a famous German scientist, suggested that it was impossible to know exactly where an electron was at all times. So last class we kind of talked about the electron being more of a wave or moving in a wave motion instead of a circular path. So if we wanted to watch an electron orbit the nucleus, this requires some kind of light. But last class we talked about that light waves have photons, and if a photon has enough energy, it can move an electron. So shining the light on an electron will move it. Electrons are so small and move so fast that we would lose where they go. We wouldn't be able to know where they are. The Heisenberg uncertainty principle says it's impossible to simultaneously know an electron's location and speed around the nucleus of the atom. Electrons travel in waves around the nucleus, and we can't be sure where they are some of the time. Schrödinger used complicated mathematics and probability to calculate where electrons were most likely to be located. This new model, so Schrödinger comes up with a new model, is called the quantum mechanical model, and it predicts the probability of where the electron is going to be 90% of the time. Okay, so here's kind of a picture of what that looks like. That red dot that's moving around really fast is an electron. All of those lighter dots are all the possible locations that an electron can go. This model is also called the electron cloud model or the 90% probability model. It means that we think the electron is located in some region or a cloud of space 90% of the time. But if we went looking for it by shining a light on it, it would move to some unpredictable location and we might not know what that location is. So that sounds kind of vague, a model where we don't actually know where the electron is, but Schrödinger did calculations to figure out exactly where in the energy levels we could probably find the electron. Those are called sublevels. Those should sound familiar. Even within these sublevels, Schrödinger figured out what shape an electron would be located when it moved. This is called an orbital. So orbitals are kind of like the shape of the path of the electron. So remember, electrons don't travel in nice circular orbits. They travel in unpredictable wave-like patterns in a 3D area. These areas are called sublevels. The electron could be there any time. It would be like taking a snapshot picture. The orbital would be a collection of all the potential snapshots. So just for example, to kind of help you out here, if I wrote down I would have energy level. From there, I could have sublevels. Within a sublevel, I would have an orbital. My electrons are in those orbitals. So just to kind of give you an idea of what we're talking about. So remember that electrons are on the outside part of the atom. They're the only part of the atom that can be added or removed. Those are what makes the atom react. Everything we know about electrons is what we know about atoms reacting. That's why we care so much about where an electron is. if an atom's reacting, that means it's usually forming some kind of chemical bond or breaking a bond. And the entire electronics and computer industry is based on understanding electrons and understanding their location and their energy and their behavior. So our first sublevel that we're going to talk about is called the S sublevel. It's the smallest one. There's not much room in our first energy level. So our first energy level only has one sublevel that the electron can be in, and it's called the S sublevel. The S sublevel only has one orbital. So again, let me just pull up this picture or this little thing I wrote. So energy level, we're talking about energy level number 1. The sublevel is S. S only has one orbital, which has 2 electrons. Okay. All right. Oh, let's go back. Okay. This orbital is shaped like a sphere, so a circular shape. Each energy level actually has that S sublevel, but our first energy level only has the S sublevel. It means that the electron is moving in a sphere. So on these pictures, there's tons of little dots. All those dots just represent where an electron can be located, but in reality, you'd only have one electron, or 1 to 2 electrons. Each energy level has an S sublevel. Each S sublevel only has one orbital, which is shaped as a sphere. Notice that it looks like if there are hundreds of electrons in each S, but it's only 1 to 2 electrons. We're looking at all the possible locations. So our first energy level can only hold 2 electrons total. Here's some pictures. As I move up energy levels, so those numbers represent energy levels, 1, 2, 3. As I move up my energy levels, the size of that orbital, or the size of that sublevel, the S, gets larger. So there's more spaces for those electrons to move. So again, in our first energy level, I only have the S sublevel, which means I only have one orbital, which means I only have 2 electrons in the first energy level. Our second energy level has 2 types of sublevels. It has an S and it has a P. The P sublevels are shaped like dumbbells. The S sublevel can only hold 1 orbital, but the P sublevel has 3. So go over here. Let me just change colors. So now if I'm talking about energy level number 2, it has sublevels S and P, which means S has 1 orbital, but P has 3 orbitals. Okay, so if each orbital can hold 2 electrons, 3 times 2 is 6, plus 2 more from the S would be 8 total electrons. Okay. Let's see. Each orbital is identical in shape except for its orientation in space. Each orbital in the P sublevel can hold a max of 2 electrons. So there's 6 electrons total in the P sublevel. Here's some pictures of what that looks like. So again, when I'm talking about a P sublevel, I'm not referring to a specific energy level. I'm just saying kind of the shape of the electron and where it's moving in space. So for P, it exists in a dumbbell-like space. Again, on that picture with the blue dots, those are just all the possible locations that the electron could be in this orbital. And then the purple ones are, again, kind of showing the shapes that they could make. Okay, here's what all the P orbitals would look like if you smashed them together. That's what that left side looks like. So I should have 6, 1, 2, 3, 4, 5, 6, and I do. The only thing that picture is missing, is the S sublevel. So again, how many total electrons can the second energy level hold? Well, I have the S sublevel with 1 orbital, and I have the P sublevel with 3 orbitals. Each orbital can hold 2 electrons, so that gives me 8 total electrons in the second energy level. Here's a picture of what that would look like. I have my S in the middle, which is that circle, And then I have all the p sublevels, which is showing, it kind of looks like little flowers, maybe flower petals. Third energy level has 3 sublevels, S, P, and D. The D sublevel holds 5 orbitals, which if each one can hold 2 times 5 is 10. This allows the third energy level to hold 18 electrons. Let's go ahead and write that down like we were. Okay, so let's see, what color do I want? Maybe red. Okay, so if I'm on the third energy level, that has an S, a P, and a D sublevel, which means I have 1 orbital on S, 3 orbitals on P, and 5 orbitals on D. If I add up all my electrons, I can have 2 electrons in each of those. That gives me 18 total electrons for the third energy level. Here's the shapes of those D orbitals. They all kind of look a little different. Each one can still only hold 2. So if I said an atom with 3 total energy levels can hold how many electrons? This would be 18, because if I'm adding up electrons for 3 different energy levels, I'm adding up this 2, this 18, and this 8. That should give me 28 electrons, because it's adding up all 3 energy levels. Yeah, so that kind of just repeats what I was saying. Okay, so to summarize all of this in a nice little box, S can hold 2 electrons, P holds 6, D holds 10, F holds 14. Some hints: any energy level N has exactly N sublevels in it. Each sublevel has a specific number of orbitals as seen on the chart that I'm about to show you. Since electrons don't like each other, they're negative, having the same charge and repelling each other, an orbital can hold a max of 2 electrons. This is called the Pauli exclusion principle. That says each orbital can hold 2 electrons. Also remember, a sublevel, the letters simply tell us where the electron is located, but the orbital tells us more about the shape that it moves as it travels in a wave. So here's a nice little chart for you. First energy level holds 2 electrons, second holds 8, third holds 18, fourth holds 32. So that's the same thing as if we were drawing Bohr models. It's those same numbers. Here's some pictures of what those sublevels and orbitals can kind of look like. So if we were to have to draw out all these orbitals, it would be really difficult and confusing, and it would look something like this, and it would take forever. So instead of doing that, we can use shorthand for where the electrons are located. There's 2 ways. We can do electron configuration, which you should have done last year, and you can do orbital diagrams. Electron configuration indicates where electrons live or where they're located. We use numbers to indicate the energy level, letters to indicate the shape or sublevel, and superscripts to indicate how many electrons there are in a particular sublevel. So let's practice what this looks like. So if I'm trying to find the electron configuration for lithium, I can look on the periodic table at the atomic number. The atomic number is 3, so I have 3 electrons. I need to start with the first energy level. So energy level number 1, that has an S sublevel and can hold 2 electrons. I'm trying to get to 3, so I have to keep going. Now I'm on my second energy level, the S sublevel, and it can hold 2, but I only need 1 more. So this 2 and this 1 add up to 3. 1s2, 2s1 is the electron configuration for lithium. And I'll show y'all kind of a shortcut for that in just a second. Always remember that electrons occupy the lowest energy level first. Because electrons are negative, they want to be as close to the nucleus as possible. that's going to be the most stable location. This is called the off-bow principle. Electrons fill the lowest energy levels first. So let's do sodium. Oops. Sodium is Na, which has 11 electrons. So I'm going to start with 1s2, 2s2. After I, remember that the energy level number 2 has S, but it also has P sublevels. P can hold up to 6. So I have 2, 4, 5, 6, 7, 8, 9, 10. And then I would go to my next energy level, which is energy level 3. The first thing it has to fill is that S sublevel. I only need one more electron, so I can put a 1. So if I add up these superscripts, those are going to add up to be 11. Okay. Again, I'll show you a shortcut for this in just a minute. Sometimes there's a violation of the off-bow principle. So if we look at potassium, potassium is K. It has 19 electrons. So let's write its configuration. We have 1s2, 2s2, 2p6, 3s2. After 3s2, we have 3p6. And then we have 4. I only need one more electron, so I can say 4s1. These should all add up to be 19. So sometimes people think that you would go after 3p, you would go to 3d, because that seems like it makes sense for numerical order. However, it's actually what we just wrote. This 4s has to come before 3d. When I show you the shortcut also, it'll make a lot more sense. So the reason we do this is because that 4s energy level in that first column is lower in energy than 3d, meaning it's easier for an electron to occupy 4s, it'd be more stable, than it is to occupy 3d. So 4s needs to come before 3d. So the d orbital is very high energy, it's unstable. Electrons in all atoms in nature instead go up to the 4s and fill that orbital first before they fill up the 3d. Even though 4s is farther away from the nucleus, it's going to be more stable. That pattern continues throughout all elements. Okay, so yeah, I'll let me see if I can show you that shortcut really fast. I think I have it over here. Okay, so your periodic table is actually arranged in these blocks, the S block, D, P, and F. So we can kind of use the periodic table as a map. So if I'm looking for, let's say lithium's up here. On my periodic table, lithium would be in row number, let's see, so it'd be like 1A, and then it would be in spot 2. I can't mark it on my slides, but I can just talk about it. So if I use this out as a map, the period number is the same as this sublevel number, that 1 and that 2. So 1, and then it's in the S block, that blue colored block, and then I can count elements. So I have 1 where hydrogen is, and I have 1 where helium is. That gives me that number 2 at the top, that superscript. Then I would go to the next period, period number 2. It's period number 2, so I wrote my big 2. It's still in the S block or sublevel, and it's the very first element, so the number 1 is that first element. Okay, if I was looking for sodium, which would be in column number 1 and then row number 3, that first one, I can do the same thing. So row 1, period 1, It's in the S block or sublevel, and then I can count my 2 elements, hydrogen and helium. Then I would go to row number 2. I'm still in that S sublevel, their block, those blue colors, and I can count 2 more elements. That's where this 2 comes from. So now I need to go all the way across my periodic table into that yellow section. I'm still on row 2, but the yellow section is the P block. So from the P block, I'm going to count how many elements I have, and there's 6 of them. That puts me to the next period number, which is period number 3. I'm back in the S block, and it's the very first element. So this is kind of like a map to get to your element. Hopefully that made a little bit more sense. I will also put a video of what this looks like in the, what's it called? In the website, so that you can get some extra help if you need, or feel free to ask a friend or come into tutorials. Okay, let's get back to our notes. Let's see. Okay, so the next way that we can kind of do shorthand is what's called an electron or an orbital diagram. It's a better way of actually seeing where the electrons are. You can draw square boxes to indicate sublevels, or you might see me just draw a line. You can do either one. Then we would draw up and down arrows to indicate electrons. So let's look at oxygen. Oxygen has 8 electrons. So we can draw our sublevels. The first one is 1s. S can hold 2 electrons, so I can go ahead and draw my 2 electrons. Then I would go to 2s. Again, I can hold 2 electrons. So now I'm at 4, but I'm trying to get to 8. So my next sublevel is 2p. Remember that p has 3 orbitals. That's why I drew 3 lines. And then I can fill in electrons. So I need 4 more electrons. You always have to put 1 in each line or each box before you can go back and pair them up. So we can check ourselves. It looks just like that. Each box represents a shape. Notice anything weird. These last 2 electrons right here are filled in separate orbitals first. This is because electrons repel each other. They want to stay as far away from each other as possible. So if they don't have to pair up, they're not going to. This is also called Hund's rule. That's important. Hund's rule. Electrons fill single orbitals first before they start pairing up. Think about if you get onto a plane. Usually, if there's not assigned seats, everyone fills up a row, or they go sit in a row by themselves. And then if everyone's already in a row, then people start pairing up. Generally, that's what happens. Okay. Also, notice that oxygen has these 2 unpaired electrons. That causes magnetism. So anytime there's electrons that are not paired up, that's going to cause magnetism. They're spinning clockwise or counterclockwise, and then they give you either a north pole or south pole magnetic field. When electrons are next to each other, like this, in the same orbital, that magnetic field will cancel out. So any element with unpaired electrons is going to be magnetic. This is called paramagnetic. So if it's magnetic in any way, it's just going to be called paramagnetic. Okay, obviously the more unpaired electrons you have, the more magnetic it's going to be. If it's not magnetic, there's another term for it, and it's called diamagnetic. So make sure you know both of those terms. So if there's no unshared pairs, it's called diamagnetic. Okay, so let's review all the different models that we've talked about in these last 4 class periods. We started out with Dalton and talking about the marble model. He thought that the atom was just a solid marble-like structure. Then we have J.J. Thomson, who came up with the plum pudding model. He just said that there are positives and negatives just kind of floating around in the atom. Next, we have Rutherford's nuclear model. Remember, he did that gold foil experiment. He realized that there's a nucleus and that all your protons are in the nucleus and electrons are orbiting. Next, we have the Bohr model or planetary model. This is when we start talking about energy levels and that there's different electrons on different energy levels. Next, we have the de Broglie model. This is where they start saying that electrons are moving more in waves. We talked about that last class. And then we have, lastly, the quantum mechanical model by Schrodinger. This is what we currently use. It's more of an electron cloud type of model. So make sure you know all of those. Make sure you know the order of those. Why is any of this important? So besides talking about it in science classes and using it for research and all of that, the atom was considered to be an imaginary thing that people just laughed at. Roosevelt trusted Einstein, and he funded his secret research project known as the Manhattan Project. In a few short years, the idea of an invisible atom had been developed turned into a city-destroying weapon, which is the atomic bomb. They figured out that they could split atoms apart and it would release tons of energy. So here's some examples of that. We have Hiroshima, Nagasaki, lots and lots and lots of people died. 90% of each city was destroyed. Only 2 atomic bombs have ever been used in wartime history, and the U.S. used both of them against Japan to end World War II. So if you wanted to look up videos of what that looks like, you can do that. Those are just atoms being split apart. Okay, guys, you have guided practice problems. It's mostly electron configuration and orbitals. So use that periodic table that I just showed you, using it as a map. I will go back to it if you want to take a screenshot of it to practice. So give me 1 second. Okay, so if you want to screenshot this, that would probably be a good idea. That'll help you with your guided practice. Bye, guys.